Okay. Okay, let's roll. All right, answer to your names, please. Barat, Lassie, Burke.
Here.
Kane is here. Dunlap.
Here.
Gallegos.
Here.
Head.
Here.
Irvin.
Here.
Medina. Sorry, Kylie Medina. Manuel Medina.
Here.
Anisi. Mossier is Mossier here. Oh, Olano. Richardson.
Here.
Sieg.
Here.
Tillman.
Here.
Rancho Pagada. Wetland. And Wright. Okay, so I was thinking about what to do today. Well, definitely what we'll be doing today is finish up that last question I messed up on. I realized what my mistake was, a very slight mistake, but made a big difference in terms of the outcome. And then I'm going to go through, I think we had 2 more questions in the assignments to complete. So we're going to go through that. And I was thinking that if you have any questions concerning the test that you just did, or if you want to come and see me tomorrow, I'll be in my office tomorrow, maybe about from 8, 9 o'clock onwards. It's not scheduled in my timetable, but I have to be here anyway for other reasons. So I figured that, I should let you know that I'll be here tomorrow in my office. If you have any questions concerning the test or any other questions concerning anything related to this course, all right? And then after that, we're going to start the next chapter, which deals with acids and bases. So with that said, let's look at this. So the mistake I made, let me just review a bit. I'm not going to go through everything from the beginning. All I'm going to say is, because there was an ice table that I created, and based on that ice table, and based on what happens at equilibrium, I said Kc to be equal to 0.0100 minus x divided by 0.00100 plus x, and all of this is squared. And the Kc value is equal to 1.2 times 10 to the 3, right? So I won't go through all the steps. Basically, this is what it comes down to. X is equal to 0.0016. And this is where I made a mistake. The mistake I made was that I had 0.016, but there should be an additional 0 here, all right? Or the x value could be equal to minus 4.5 times 10 to the minus 3. And if you remember, I said that this cannot be feasible or, can't work because there's no such thing as a negative concentration, right? So therefore, to find the concentration of CO, which would be equal to the concentration of CO2, that would be equal to 1.00 times 10 to the minus 3 plus 0.0016. And according to my calculation, this works out to be 0.0026 m. And then the concentration of COCl2 will be equal to 0.0100 minus m, and this should be all m here, by the way, minus 0.0016 m. And according to my calculation, this works out to be equal to 0.0086 0.084M. But we're not finished there because the question is asking for the moles of each substance. What we have so far are the concentrations, right? So let me do this up here. We squeeze this up here. So the number of moles of CO will be equal to the number of moles of chlorine, which will be equal to the molarity, which is 0.0026M multiplied by the volume. And what's the volume? 10.0 liters. So 10.0 liters, and that gives you 0.026 moles. And then for the COCl2, the number of moles of COCl2 would be equal to the molarity, which is 0.0084 M multiplied by 10.0 liters, and that would be equal to 0.084 moles. And that's basically how that is done. All right. Okay. Any questions about this? Any questions? Any questions? Questions? Okay, so let's go to the assignment. Let me see if I can bring it up here. Okay, so assignments, and this is number 3. Okay, so number 7, 8. Oh, we did number 7 already, right? Okay, all right. So we're going to proceed with number. Wait, did we do number 8? We started off number 8. Okay. Let me just see what's following. Okay, this should be number 9. That's a typo there. Okay, so just 2 more questions. All right, so let's move on to number 8. So if I remember correctly, we went as far as the B part, right? Or the A part, and that's it?
The B part.
The B part, okay. So let's move. Okay, what was the answer for the B part? Because we need to know that before we can do it shifts to the left. All right, so that's kind of important for us to know. So shifts shifts to the left. All right, so let's see now. For the C part, the question is asking, what will the concentration of SO2 be when the system achieves equilibrium? All right, so we're going to need, in fact, I need to scroll back up to look at the numbers. Okay, so, I need the answers for the, let me see here. I need the answer for the A part. We did the calculation of Q, right?
Mm-hmm.
So what was Q?
0.096.
Okay, so Q is equal to 0.096, right? And here we said that Q is not equal to KP, right? In fact, this is Q and KP is this. So that tells us that QP is greater than KP. All right, so we need these numbers here. The 30 for the SO2, the 0.16 for the chlorine, and the 0.5 for the SOCO2. So basically, all right, let me just erase some of this stuff here. So basically, we can say that QP is equal to PSO2 times PCl2 divided by PSO2 Cl2, right? And then when we put the numbers in, for SO2, it is 0.3. Oh, we did that already. So what we need to do now is basically create an ice table. All right, so I don't know why I'm getting confused about this here. So basically we need to create an ice table where we have SO2, CO2 to give SO2 plus CO2. So initially, we're going to have 0.50 atmospheres for the SO2, CO2. For the SO2, it's 0.30 atmospheres. And for the chlorine, it's 0.16 atmospheres. And since we know that the reaction is going to shift to the left to achieve equilibrium, then what we're going to do is say that because the reaction is, what's going on with this here? Because the reaction is going to shift to the left, that means that some of the SO2 will react with some of the CO2 to give some SO2, CO2. So the change here would be minus X for this, minus X for this, and plus X for the SO2, CO2. So by the time we reach equilibrium, okay, I'm going to squeeze this down here. You're going to have 0.50 plus X. Here we're going to have 0.30 minus X, and here you're going to have 0.16 minus X, all right? So basically, oops, I accidentally erased something. What did I erase? I erased part of the X here. Okay, I think that's it. So basically, Kc will be equal to 0.30 minus X times 0.16 minus X divided by 0.50 plus X, and that is equal to, what was the Kc, 0.011?
Yeah.
0.011, right? So from there, basically it's all algebra, and I did the solution here so as to save time. So basically, I'm going to go through the steps in this case. All right, let me just clear all this here. This is looking a bit disorganized. Let me scroll down so we have enough space to work with. Okay, so I'm just going to rewrite the ice table. SO2, CO2 to give SO2 plus CO2. And I had here 0.50 initially, 0.30 initially, and 0.16 initially. The change here is going to be, because it's going left, plus X here, minus X here, minus X here. So at equilibrium, you're going to have 0.50 plus X. You're going to have 0.30 minus X. Here you're going to have 0.16 minus X. So Kc is equal to 0.30 minus X times 0.16 minus X. And down here, you're going to have as a denominator 0.50 plus X, right? And then, and this would be equal to 0.011. So of course, we have to solve for X based on what we have here. So what we would do is cross multiply to get 0.30 minus X times 0.16 minus X. And then this would be equal to 0.011 times 0.50 plus X. And then you expand this here. When I did that, I got 0.048 minus 0.030 X minus 0.16X plus X squared. And then in this case here on the other side, I'll distribute, and that results in 5.5 times 10 to the minus 3 plus 0.011X. And then I'll add these two together to get 0.048 minus 0. This should be 0.3, not 0.03. So this should be 0.30. So when you add these two, you're going to get minus 0.46x plus x squared equals to 5.5 times 10 to the minus 3 plus 0.011x. And this will simplify. I'm going to jump some steps here. But you're going to get this quadratic equation right here. X squared plus, minus 0.047 x plus 0.043 equals to 0. So basically you go through some steps and you end up with this quadratic equation. And then when you solve for x, there'll be two possible values. One of them is going to be 0.35 and the other one is going to be 0.012. Now, unlike the example that we just looked at in the PowerPoint, remember in that example, we had two possible values, one negative and one positive. So it was easy for us to decide on the positive value because, as we said before, you can't have a negative concentration. In this case, you have two positive values. So the question now becomes, which one would be the correct one? And the answer lies in this part right, actually this part right here. X has to be less than 0.16, right? Because 0.16 minus x has to be a positive number. So the only possible answer that would fit that particular requirement would be x equal to 0.012 because it's less than 0.16, right? Yes, ma'am.
You said 0.012, but you wrote 0.12.
Sorry?
You said 0.012, but you wrote.
No, 0.12, I'm sorry. Yeah, my bad, 0.12. Yes, so that's a value we choose because that's the only value between these two that is less than the lowest 0.16 value right here, right? So basically, to find the concentration, no, the question is asking specifically for the concentration of SOCl2. This represents, X represents the change in the pressure, right? So the pressure of SOCl2 would be equal to this right here, 0.50 atmospheres plus 0.12 atmospheres, and that will be equal to 0.62 atmospheres, right? And then that's a pressure, but the question is asking for the concentration. So my question to you is, what's the relationship between the concentration of a gas and its pressure? You should remember that from your gas laws back in Chem 1. The ideal gas law, exactly, which is PV is equal to nRT, right? And we can rearrange it to get P is equal to N over V times RT. And N over V, you should recognize as the concentration of the gas, right? So to find the concentration, let me squeeze this in here. To find the concentration of the gas, that is going to be equal to P divided by RT. So that will be equal to P, which is 0.62 atmospheres, divided by R, which is 0.0821 liters atmospheres, over a mole Kelvin times the temperature. What's the temperature? Somewhere. 300 Kelvin. And that's it. And when I did that calculation, I'm just going to show it there. I got 0.025 M as the pressure of the gas. And that would be the final answer. All right. Okay, any questions about this particular? Yes, sir.
X squared all the way to the top right.
I'm sorry?
Is that when you wrote x squared is equal to 0.047x? Is that supposed to be?
Okay, where are we talking? Oh, you mean here?
Yeah.
Okay, right. That comes from this part right here. I skipped several steps. Right, so I mean, I can show you, if you come to my office, then I'll show you exactly what to get from there to there. I just decided in the interest of time just to skip over the steps. But it's all algebraic, manipulations, right? So that you get the equation in the form of a quadratic equation, and then you can figure out what the two possible x would be. Okay, any other questions? Any other questions? Yes, ma'am.
Equals that.
Hmm?
Why is it P is equal to 0?
Why is it p equal to?
Why'd you put P?
You mean here?
Yeah, here.
Because that's what the question is asking for. I'm sorry, concentration. So that would be concentration of the gas. Thank you. So this here would be concentration of the gas, not pressure. Concentration of the gas, that's what that should be. All right, any other questions? Any other questions? Yes, ma'am.
Now, when you get to the part of the quadratic formula and you're choosing between 0.35 or 0.12, can you explain your reasoning behind that?
Because of this right here. X can be only less than 0.16. It cannot be greater than 0.16, right? Because there's no such thing as a negative concentration. So therefore, the only of the two values of X that we solve here, only this one would be the valid one for the purposes of this question. Right? You can't have a negative concentration, so that X cannot be 0.35. All right? Okay, any other questions before we move on? Any other questions? Any other questions? Okay, so let me clear this and scroll down to the last question. Okay, so this question is asking for you to calculate the concentrations of all the components that are present, and it gives you the Kc value, and it gives you the initial concentration of PCl5. So again, istable setup is required. So the change, we're going to say that the change is minus X for PCl5 plus X for PCl3 and plus X for Cl2. So at equilibrium, you're going to have 1.00 minus X, going to have X, going to have X. So Kc is equal to the concentration of PCl3 and the concentration of Cl2 divided by the concentration of PCl5. And then we put the terms in. We're going to have X times X over 1.00 minus X. So this would be equal to X squared over 1.00 minus X. And that would be equal to 0.0013. So again, some algebras will be involved. So we can do this. X squared is equal to 0.0013 times 1.00 minus X. And this will be equal to 0.0013 minus 0.0013x. And then we write it down in the form of a quadratic, x squared plus 0.0013x minus 0.0013 equals to 0. And I think I have that done here. So when I solve for this, and I don't remember if I had two values here, but the value that is correct is 0.035 for X, right? So the concentration of PCl5 would be equal to 1.0 minus X, so that's 1.00 minus 0.035. And that is going to be, and this of course is M and M units. And when I work that out, I got 0.97 M. And then for the concentration of PCl3, that is going to be equal to the concentration of Cl2. And that is going to be equal to X, which is 0.0035 M. So those are the answers. I think I added 1 0 too many. (0.035 M). All right. And that's basically how that is done. Okay. Any questions about this one? Questions? Any questions? No questions? Okay, so before we move on to acids and bases, any questions in particular about the test, right? Any area of difficulty? By the way, I've posted, I didn't realize until this morning that I neglected to post the answer key. So I posted it in Canvas in a folder labeled here. I take it I can clear this, right? Okay, so I have posted the answer key in this folder right here, test answer keys, and that's it right here. All right, so you may want to download it and look at it and compare it to your test. And if you have any questions, if you want to dispute anything, you can come and see me about that. All right. So any questions about the test, or should I just move on to acids and bases? Okay, so let's talk about acids and bases. So I think you should have been introduced to acids and bases in General Chemistry 1. So you should be familiar with some of the properties that are displayed by the substances. All right, so as far as acids are concerned, these are the properties. They have a sour taste, and please, even though I'm telling you it has a sour taste, that doesn't mean that you should try and taste it in the lab, all right? Even though I'm quite sure you're familiar with, for example, citrus fruits, lemons, oranges, and so on. They have a characteristic sour taste, and that's due to the presence of citric acid in those fruits. Vinegar also has a sharp sour taste, and that's due to acetic acid that is present, all right? They react with certain metals, and this is actually true for the more active metals to produce hydrogen gas, and they react with carbonates and bicarbonates to produce carbon dioxide gas, all right? So those are just some properties displayed by acids. And then as far as bases are concerned, they have typically a sharp, well, not really a sharp, but a bitter taste. Again, please do not taste any bases in the lab to find that out for yourself. They tend to feel slippery. And again, I would recommend that you try this in the lab. But basically what happens is that the base contains hydroxide ions, which will react with the oils that would be on your skin, and it transforms them into, believe it or not, soap. So that slippery feel that you would get when you handle base, or if you get some bases between your fingers, that's due to the formation of soap when the base reacts with a group of compounds known as triglycerides that you'll find in oils, right? The oils produced by your skin. Okay, so let's talk about the different definitions of acids and bases. So the first one we're going to talk about is by a guy by the name of Arrhenius, a very important chemist, made a lot of discoveries now we take for granted. He came up with a definition of acids and bases. And according to his definition, an Arrhenius acid is a substance which, when added to water, produces H plus ions. And you see here in parentheses H0 plus ions. You can use this or this interchangeably. In fact, this is more realistic or more representative of what actually happens when you add an acid to water. It forms hydronium ions, right? But it's okay for you to use H plus ions as well, as long as you put aqueous here beside it. So this is what an acid does, right? When you add it to water. And this is basically showing you one example of that. HCl is acidic. When it's added to water, the hydrogen here from the acid is transferred to the oxygen of the water, and it forms a hydronium ion, and the chloride ion is left by itself, right? So that's basically an example of an Arrhenius acid, or an acid behavior according to Arrhenius. Arrhenius also came up with a definition of the base, or of a base. He said that a base is a substance that, when added to water, produces hydroxide ions. And there are several examples we can look at. In this example here, we have ammonia added to water, and it forms the ammonium ion. And the ammonium ion is formed as a result of the transfer of one of the hydrogen ions here from the water to the nitrogen here. So that's how you get the ammonium. And then you have the hydroxide ion being produced, all right? So that's what a base does. When added to water, it produces hydroxide ions according to the Arrhenius definition, all right? Now, another definition for acids and bases is what we call the Bronsted. In some textbooks, they call it the Bronsted-Lowry definition of an acid and a base. So according to Bronsted, an acid is what we call a proton donor. And what it means is that basically it gives up a hydrogen ion to something else. And that something else, according to the Bronsted definition, is the base, because according to Bronsted, a base is a proton acceptor, all right? So an example is shown here, where you add ammonia to water, and what happens, and we saw this earlier in the previous slide, where the hydrogen is transferred to the ammonia, specifically to the nitrogen, to form your ammonium and the hydroxide ion, right? So in this particular case, the water would be the acid because it's giving up a hydrogen ion, which is also known as a proton. I probably should have mentioned that. So let me just write a little note here. Whenever you see the term proton, that's basically the hydrogen ion, because remember the hydrogen atom has only one electron. You remove that electron, the only thing that's left is a proton, right? So whenever you hear the term proton, it's the same thing as a hydrogen ion, right? So that's what's happening in this particular case. The water here is acting as an acid because it's giving up a proton to the ammonia, which means that the ammonia is going to be the base according to the Bronsted definition, all right? So that's the difference between the Bronsted definition and the previous definition that we saw by Arrhenius. Arrhenius said an acid is a substance which produces hydrogen ions in water. A base is a substance which produces hydroxide ions in water. So those definitions are based on the properties displayed when the substance is dissolved in water. In this case, the definition is based on the proton transfer, what gives up a proton and what accepts a proton, right? The substance that gives up the proton is called the acid. The substance that accepts the proton is called the base, right? Now, as far as the products are concerned, there are some other terms that we use for those products according to the Bronsted definition. And in the case of the product resulting from the loss of a proton, that is called the conjugate base, right? So the acid gives up a proton, and what is left is called the conjugate base, right? On the other hand, the base, which accepts a proton, it forms what is called the conjugate acid, all right? So the acid forms a conjugate base by the loss of a proton, while the base forms a conjugate acid by the gain of a proton. So you'll hear terms like conjugate acid-base pairs, right? Basically, we're talking about the pair of species where one is the acid and the other one is a conjugate base, or vice versa, all right? So those are some additional terms that you need to be aware of, all right? Okay, so let's get into assignment number 4. Get started on this. Oops. That's for you. Yes, sir. Yes, ma'am, sorry.
Is it gonna be due tonight?
Oh, good question. Tomorrow. In fact, thank you for reminding me. Let me set up that Dropbox now. Take what I'm passed down.
And you're posting the PowerPoint for this? It's
Okay, yes, I'll do that. Take what I'm passed down. Take what I'm passed down. Okay, so let me create that Dropbox for assignment number 3. Right now, before I forget, mind me. All right, so let me go here, assignments. 3. Okay, so tomorrow is the 15th. July. 5. available from today. Okay, so now you should be able to submit your assignment number 3 and the PowerPoint for this chapter. Publish that now. So this is where is it? Yeah. Okay, here it is. Okay, so I've just published today's PowerPoint. All right. So let me also publish assignment 4 for you guys out there in Zoom. And let me open it up now. Oops, why did I do that? Okay, so the first question is based on what we just covered, right? Label the acid, base, conjugate acid, and conjugate base in each of the following reactions. Now remember what I said. The acid, and this is according to Bronsted definition. The acid is a substance which gives up protons. The base is a substance which accepts protons, right? And when the base accepts protons, it forms the conjugate acid. When an acid gives up protons, it forms the conjugate base, right? Those are the things you have to remember to answer these questions. So let me turn on my writing function here. Okay, so let's look at the first one. What say you is H2SO4? Is it an acid base, conjugate acid, or conjugate base?
Acid.
Acid, right? And the ammonia is base, right, exactly. So HSO4 minus, what is that? Conjugate base, all right? Everybody see why that is so? Because the HSO4 is formed when H2SO4 loses the hydrogen ion, right? Which means that this is what? Ammonium.
Conjugate acid.
Conjugate acid. Very good. Okay. What about B?
That an acid?
Okay, so that's the acid. And water would be the
Base.
base, right? So H3O plus. What is that? Conjugate acid. And this would be obviously the conjugate base. Okay, very good. Now this one might be a bit confusing, but the same principles apply, all right? So what do you think this is?
Base.
Exactly. And this would be the, okay, so what would this be?
Conjugate base.
Conjugate base. Because you're losing the hydrogen, even though the sodium is there, but the key thing is that the hydrogen is being lost and you end up with the chloride ion here, which means that this is what? What's this? The last one.
Conjugate acid.
Conjugate acid, all right? Okay, very good. Any questions about these? Any questions? Any questions? All right, let me clear this and scroll down to number 2. Now, in the case of number 2, they gave you certain compounds, certain acids, and you're to write down the formulas for their corresponding conjugate base. So let's start off with HI. What do you think the conjugate base of hydroiodic acid is? Now remember, the conjugate base is formed as a result of the loss of a hydrogen ion or proton, right? Okay, so you need to keep that in mind to answer these. So what's the answer for, A?
Just be I.
I what?
Minus.
I minus. Right? Because when you lose a hydrogen which is positively charged, then you're going to have a negative charge left behind on the I. What about NH4 plus? What would be the conjugate base of NH4 plus? NH3 is indeed correct. Okay, what about H2CO3? What would be the conjugate base of that formula? H
CO3
CO3
minus.
minus, exactly. And what about HNO3? What would be the conjugate base of that? NO3 minus. Okay, very good. All right, so that's number 2. Now number 3 is, it's kind of like the opposite. Oh, I'm sorry.
What's the sign for the NH3?
No,
It's
sorry,
still positive.
because it's positive to begin with, and the H plus is being lost, which is positive, so therefore what's left behind would be a neutral molecule. You see what I'm saying? The ion before has a plus charge,
Mhm.
right? You're removing something that has a plus charge, right?
Yes.
So therefore, what is left behind will have no charge.
Okay.
You see what I'm saying? So therefore, the molecule is neutral. Okay, any other questions before we move on to number 3? Any other questions? Yes, sir.
Because all these other ones have no charge, they just become negative because they lose a hydrogen.
Exactly. All right. Okay, so number 3 is kind of like the opposite of what we did in number 2. In this case, they're giving you different bases and they're asking for the conjugate acid. So in this case, the opposite is going to occur. You're going to add a hydrogen ion to form the conjugate acid, right? So with that in mind, what would be the conjugate acid for Cn minus?
Yeah.
No, not Cn. HCN, exactly. You're adding a hydrogen ion to whatever is there, and that's the conjugate acid. Okay, what about O2 minus? Will be HO
Minus.
minus, exactly. Get a question?
The HCN turn into a positive or just neutral?
No, it's neutral because you're adding something that is positive to something that is negative, so therefore it's going to be neutral. C.
H4COO.
Okay, even though traditionally we would put the hydrogen here, but for now I'll just accept this as the correct answer. All right, and let me clear this here and scroll down. I think there's one more. Okay, NH3. Exactly, NH4 plus would be the answer. Okay, very good. All right, and I take it there are no questions for these, right?
Excuse me.
Yes, ma'am.
For C, does it become a neutral or does it?
It becomes neutral, right, exactly. Okay, so let me see if we can do anything after this. Okay, we can do that right now. So back to the PowerPoint we go. Okay, so let's see here. Okay, so keeping in mind what we said about Bronsted, the Bronsted definition, we can look at the acid-base properties of water. Now, it turns out that water by itself, if you have pure water in a container, if you have pure water in a container by itself, then it will undergo a process known as autoionization, all right? And basically what that means is that the water molecule will dissociate itself to form H plus and OH minus. So that is represented by this equation. Another way of representing this in terms of an equation is we could have 2 water molecules forming H3O plus OH minus, all right? So this is just another way of saying the same thing, all right? And this happens pretty much under normal conditions. Okay, so this happens under normal conditions, and this is showing you more explicitly what is happening here. And it turns out that this is actually an acid-base reaction according to the Bronsted-Lowry definition, right? So basically, what is happening is that one water molecule will be acting as a base, and the other water molecule will be acting as an acid, right? So in this particular case, this water molecule here will be acting as the acid. This water molecule here will be acting as a base. And the reason why I say that is because this hydrogen here will be transferred to this oxygen, and you end up with the hydronium ion here. And what will be left after that transfer, in addition, would be the hydroxide ion, right? So this is, according to the Bronsted-Lowry definition, an acid-base reaction, all right? And you can identify not only the acid and the base, but also the conjugate acid and the conjugate base on the other side. So in this particular case, this hydronium ion would be the conjugate acid for this water molecule, and the hydroxide ion will be the conjugate base for that water molecule, all right? So that's the autoionization of water. And you'll notice it's a back and forth, right? So basically it's an equilibrium system, and we're going to say more about that shortly, all right? In fact, in relation to what I just said, we can write down an equilibrium expression for this system, right? Just like any other system in equilibrium. Concentration of the products divided by the concentration of the reactants. Now, in the case of this system here, because H2O is a liquid, if you remember, we said that when it comes to pure solids and liquids involved in equilibrium systems, we can pretty much ignore them. So basically, what is done here is that, and the reason for that, of course, is that the liquid, in this case, which is water, is constant. So therefore, we can rewrite this equation like this, Kc times H2O. That is a collection of constant, we call that Kw, and Kw is equal to the product of the concentration of H plus times that of OH minus. And Kw is given a special name. It's called the ionic product constant for water. And this is basically the product of the molar concentrations of the hydrogen ions and hydroxide ions at a particular temperature. And the standard temperature that we use in terms of measuring the Kw value is 25 degrees. And at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the minus 14. And of course, again, like any other equilibrium constant, we're not concerned about units. Remember I said that for Kc and Kp, we don't need to worry about the units. The same is true for Kw. Don't need to worry about the units as far as Kw is concerned, right? Now, if in the case of pure water, because there's nothing else, we know that the concentration of H plus is equal to the concentration of OH minus. So based on that, we can determine what the concentration of either of these would be. All we have to do is set this being equal to the concentration of H plus squared is equal to 1.0 times 10 to the minus 14, which means that the concentration of H plus is equal to 1.0 times 10 to the minus 14. I'm sorry, times 10 to the minus 7 m, because you'd have to find the square root of this, square root of that. So therefore, the concentration of H plus is equal to 1.0 times 10 to the minus 7, which is also equal to the concentration of OH minus, right? So basically, water is said to be neutral because the concentration of H plus is equal to the concentration of OH minus in pure water. And that is true not only for water, but for any solution that is neutral, right? Any solution, any aqueous solution that is neutral will have the concentration of H plus being equal to the concentration of OH minus. Now, if you have a situation where a solution is such that the concentration of H plus is greater than the concentration of OH minus, then we say that that solution is acidic. If the situation is reversed, if the concentration of H plus is less than that of OH minus, then we say that the solution is basic. So basically, when it comes to aqueous solutions, with regards to the concentration of H plus as it relates to OH minus, there are three types: acidic, basic, or neutral. All right. Neutral will have both of them be equal to each other. Acidic, the concentration of H plus would be greater than that of hydroxide. Basic would be the other way around, where the concentration of OH minus is greater than that of H plus. Okay, so let's look at this example. The question is asking, what is the concentration of OH minus in a hydrochloric acid solution whose hydrogen ion concentration is 1.3 m? So as we said before, Kw, in fact, I think I have the answer. Hold on. Let me clear this here. Let me see here. Okay, so remember now, Kw is equal to the concentration of H plus times the concentration of OH minus, which is equal to 1.0 times 10 to the minus 40, right? Now the question gives you the concentration of H plus, so we have to rearrange this equation to find the concentration of OH minus. That would equal to Kw divided by the concentration of H plus, and all we have to do from here is to plug numbers in, and this is the result. The concentration of OH minus is going to be equal to 7.7 times 10 to the minus 15 m. And that's how that is done. All right. So that's a relatively simple example. Okay. So let's talk about pH, which is a quantity that is a measure of the acidity of an aqueous solution. And here's the definition. This is the definition of pH, right? The pH of a solution is equal to minus log of H plus, all right? And most solutions will have a pH which ranges from about 1, which would be the lowest. Well, you can actually have values lower than that, right? But usually the lowest value is 1, and it can go up to 14, all right? So that's the definition of pH. Now, if you want to find out, let's say you're given the pH of a solution, and if you want to find out the concentration of H plus, then that would be equal to 10 to the minus pH, right? So if you want to find the concentration of H plus and you're given a pH value, this is the way you go about it. If on the other hand, you're given the H plus concentration, you want to find the pH value, then this is what you're going to use. Another thing I want to mention too, when it comes to using the log function for pH, and later on you're going to learn about pOH and some other P items, you have to be careful when it comes to rounding off to the correct number of sig figs and how you express your answer when it comes to the pH related to the concentration of H plus. So this is it. Whatever the number of significant figures here, let's say that is equal to X, then the number of decimal places would be associated with the pH calculated. So if you have X numbers of significant figures, then the number of decimal places for the H plus, I'm sorry, let me repeat that. If you have X number of significant figures for the concentration of the H plus, then the number of decimal places for the pH must also be the same as the number of significant figures here, right? So for example, I'm just going to create an arbitrary example. Let's say that the concentration of H plus is equal to 1.5, or let me just say 0.15 m, right? So what you would do is do your thing on the calculator. So the pH will be equal to minus log of 0.15 m. So that would be 0.15 log minus, so on my calculator, I got 0.82. So then 0.82 and some other digits. So the number of decimal places here would have to be 2 decimal places, which would be 0.82. And that's how you round off when you do the pH calculation based on the number of significant figures in the concentration value, right? Okay, so that's the pH. So as it relates to the acidity and basicity or neutrality of the solution or of any solution, if the solution is neutral, these two will be equal to each other, which means that the concentration of H plus will be equal to 1 times 10 to the minus 7 m, which means that the pH is equal to 7, right? So all neutral solutions will have a pH of 7. Now, if the solution is acidic, as we said before, the concentration of H plus is going to be greater than the concentration of OH minus, which means that the concentration of H plus will be greater than 1 times 10 to the minus 7, which also means that the pH of the solution will be below 7. All right. And if you understand this, then you should be able to understand what will happen as far as basic solutions are concerned. If the solution is basic, then the concentration of H plus would be less than that of OH minus, which means that the concentration of H plus would be what? What would happen to the concentration of H plus if, in terms of the value of H plus relative to the neutral solution? It's going to be what? Less than 1 times 10 to the minus 7, right? Which means that the pH is what? Greater than 7, right? So all acidic solutions will have a pH less than 7. All basic solutions will have a pH greater than 7. And all neutral solutions will have a pH equal to 7 at 25. And these are all at 25 degrees, right? Things change a bit when the temperature varies from that, all right? Okay, so it's very important that you understand the relationship between pH, concentration of H plus and OH minus, right? So basically the pH increases for a solution. That means that the concentration of H plus will be decreasing, which means that the concentration of the OH minus, let me do that here, concentration of the OH minus will be increasing, all right? So that's the relationship between pH, concentration of H plus and concentration of OH minus. Okay, any questions so far? Any question? Any questions? Okay, now how do we measure the pH? There are two ways of measuring the pH that is done in labs all over. One more accurate than the other, right? The less accurate way, and there's some instances where you don't really need an accurate pH measurement, right? The less accurate way is by using what are known as indicators, right? Indicators are basically dyes which takes on a particular color depending on the pH of its environment. So if you add the dye to a solution, it will take on a particular color. The most common one that we use here is litmus. Litmus, when you put it in acid, it becomes red. When you put it in base, it becomes blue. And that is like, it doesn't really give you any values, just, if you want to know if the solution is acidic or basic. There are other indicators which gives, and these are commercially made, which basically takes on different colors at different pHs, right? And usually, and I think there's one experiment that you guys are going to do, for those of you enrolled in my lab, where you're going to compare this strip, which has the pH, that has the indicator, to a color scale so that you can tell what their approximate pH is, right? So we use indicators for approximate measurements of pH. Now, for more accurate measurements, we use what is known as a pH meter, and there's a picture of one here, and we have pH meters upstairs. And basically it consists of, well, in this case, it has 2 electrodes. The one that we have here has 1 electrode that you basically dip in a solution and you just look at the readout on the screen. And typically these would give you a pH measurement of up to 2 decimal places, right? And that's a more accurate way of measuring the pH of a solution, all right? And here there's a table which gives you an idea as to what we're talking about in terms of the pH of different substances. And we talked about the sharp sour taste associated with acids. Acids have pH below 7, and we see that in the case of lemon juice here, vinegar here, grapefruit juice here, orange juice here, and the gastric juice in your stomach. I'm quite sure you learned in your biology courses that one of the contents that you'd find in your stomach is hydrochloric acid, which helps with the digestion of breakdown of, if I remember correctly, fats and other types of foods. And then we have some other values here. Urine has a wide variety, presumably because of what you may consume, which ends up in your urine. So it can be of a pH as low as 4.8 and a pH as high as 7.5. Water exposed to air, 5.5. Water typically has a pH of 7, pure water that is. When it's exposed to air, typically it will dissolve gases from the air. One of them will be carbon dioxide, which is acidic. So as stated down here, basically carbon dioxide, when added to water or when it dissolves in water, forms an acid known as carbonic acid. And then we have some other liquids. including pure water, which is 7, as I said before. Blood has a pH somewhere between 7.35 and 7.45, and so on and so forth. And household ammonia, which is very basic, has a pH of 11.5. Okay, now another P term that you need to be aware of is what is called POH, right? And the definition of POH is given right here. The POH is equal to minus log of the concentration of OH minus. And again, as we said in the case of pH, if you want to find the concentration of OH minus and you're given the POH, then that would be equal to 10 to the minus POH, all right? So you have pH and you have POH, right? So you might be wondering if there's any relationship between the two. Well, yes, there is, right? Going back to this equation, where the concentration of H plus times the concentration of OH minus is equal to Kw, which is equal to 1.0 times 10 to the minus 14. If you were to find the minus log of both sides, right? So minus log of this side equal to the minus log of this side of the equation, right? Which is minus log of that, then this is what you're going to end up with, right? And you should recognize that this here is basically the same as pH. This here is POH. So therefore we can say that pH plus POH for any solution is equal to 14.00. So this is true for any aqueous solution, right? The sum of the pH and the POH is equal to 14.00, all right? So that's a relationship between pH and POH, and that's a very important relationship that we'll be using in the near future. Okay, any questions so far? Any questions? Any questions? Okay, so here is an example. It gives you the pH of rainwater collected on a particular day, and the question is asking for what's the concentration of H plus ions present. So remember I said that concentration of H plus is equal to 10, or hold on, do I have this? Oh, yes, I do. Okay, so I keep forgetting that I have these solutions here. So we know that the pH is equal to minus log of H plus, and as I said before, the concentration of H plus is equal to 10 to the minus pH, right? So all you have to do now is put this value of 4.82, where the pH is in this formula, right? And then do your number crunching on the calculator, and you're going to end up with your answer being 1.5 times 10 to the minus 5 m as your answer that the question is asking for. All right, so that's a relatively simple example. All right, and remember also, let me stress this again, whatever the number of sig figs here, the number of decimal places must be the same here, right? So since you have 2 sig figs here, you have 2 decimal places here, all right? Okay, any questions about this example? Any questions? Any questions? Questions? All right, another example. The concentration of OH minus in a blood sample is 2.5 times 10 to the minus 7. So what is the pH of the blood? How would you tackle this problem? What formula would you use to calculate the pH of the blood? Let me just say that this is the 2-step process. They gave you the concentration of OH minus and they're asking for the pH. So what would be your first step?
Find POH.
Okay, so to find the pOH, you're right. To find the pOH, that's equal to minus log of 2.5 times 10 to the minus 7 m, right? Well, we don't need the m there. So let's see what that gives. 2.5 times 10 to the minus 7, and then I do the log of that, and then the minus. Okay, so what I got now, because this is 2 sig figs, oops. Because this is, come on. Oh, because this is 2 sig figs, that means the answer I have must be recorded to 2 decimal places. And this is what I got, 6.60, all right? So that's POH, right? But the question is asking for the pH, so what would be the next step?
You do 14 minus.
Okay, so pH will be equal to 14.00 minus 6.60, I'm sorry. And that would be equal to according to my calculations, 7.40. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? All right, let's move along. Let's just skip all that there. Okay. So let's talk about electrolytes. And again, this is something that you should have met in your Chem 1. You should have learned that electrolytes are basically compounds which, when added to water, can allow an electric current to pass through it, right? And the reason why this happens is because these compounds, when added to water, dissociates and form ions, all right? So what we're going to talk about, and again, this is something you should have learned in your Chem 1, we're going to talk about the difference between a strong electrolyte and a weak electrolyte. And as stated here, a strong electrolyte will undergo a 100% dissociation. So what that means is that if you have an ionic compound that is a strong electrolyte, such as sodium chloride, and you add it to water, right? Then all of the compound will dissociate and form sodium ions and chloride ions. So if you could see the particles in a solution, the only thing you're going to see are sodium and chloride ions floating around, and of course water molecules floating around in a solution, right? So that's what we mean by a strong electrolyte. And you'll notice that we use a one-directional arrow here to show that the dissociation is complete. So basically what we're saying is that the sodium and chloride ions will not recombine in solution to form the original solid, all right? So that's true for all strong electrolytes, right? Now, a weak electrolyte will undergo what is called partial or incomplete dissociation. So what does that mean? That means that not all of the original compound, when added to water, will form ions. So a good example of this would be acetic acid. Acetic acid is a weak electrolyte because when you add acetic acid to water, only a small fraction of the acetic acid molecules will undergo dissociation. So if you could actually see the particles floating around in solution, you will see mostly acetic acid molecules intact, right? And very few of the acetate ions or the H+ ions floating around, all right? Now, so that's the difference between a strong electrolyte and weak electrolytes, right? And, let me just say that in the case of weak electrolytes, it does not allow an electric current to pass through quite as easily as in the case of strong electrolytes, right? So strong electrolytes is a very good conductor of electricity, but weak electrolytes are not as good. They do conduct electricity, but it's not as good a conductor of electricity compared to strong electrolytes. Okay, so let's talk about the term strong acids, right? Strong, in the case of relating to strong acid, means the same thing as it relates to strong electrolytes, right? Basically, they will undergo complete dissociation. So a good example of a strong acid is hydrochloric acid, because when you add HCl to water, this is what happens. All of the hydrochloric acid molecules will be converted to hydronium and chloride ions, right? So again, as in this case here, you'll notice that there's a one-directional arrow here, which shows that basically the reaction is going in one direction. You will not have the hydronium and the chloride coming back together to form HCl in the aqueous solution, all right? A weak acid would be, an example would be, this is another example of a strong acid, nitric acid, right? Again, undergoes complete dissociation, and perchloric acid. So these are all examples of strong acids. And if you were in my lecture before, I don't see anybody here from my lecture, from Chem 1, I always tell my students that there are 6 strong acids that they need to remember, right? And these are the strong acids. Since you guys are new to me, relatively speaking, I'm going to write them down for you. HCl, aqueous, HBr, aqueous, HI, aqueous, HNO3, aqueous, perchloric acid, HClO4, and this one, sulfuric acid. So these are 6 strong acids that you need to commit to memory. right? Very important. You need to commit to memory these 6 strong acids. And let me just say that, these 3 here are easy to remember because they are acids of group 7, right? Chlorine, bromine, and iodine, right? So basically, once you remember these, then basically you have to focus on remembering these 6 other acids as being strong acids, right? All other acids that you're going to encounter, you can assume them to be weak acids unless you're told otherwise, right? But you need to remember that these acids are strong acids, right? And let me just say something about sulfuric acid. Because as you notice, unlike the other acids, sulfuric acids have 2 hydrogen atoms here, right? So, let me just get out of this for the time being. And let me create a Word document here. So in the case of sulfuric acid, there are 2 dissociations that can happen for every molecule of H2SO4. So let me go here. So H2SO4, H2SO4, when added to water, will undergo a strong dissociation to form H3O plus HSO4 minus, right? So the first dissociation is strong, right? So what that means, all of the sulfuric acid will be converted to these ions, right? However, in the case of HSO4 minus, when that reacts with water, undergoes a partial dissociation to form SO4 2 minus and H3O plus. So the second dissociation is weak, right? So sulfuric acid is kind of unique among those 6 acids I gave you, right? Where it has 2 hydrogen ions that it can release when it reacts with water. The first dissociation producing the first hydrogen ion will be a strong dissociation, but the second one is going to be weak, all right? And the reason why the second one is weaker than the first dissociation is because in the case of the first dissociation, you're pulling a hydrogen atom from something that is neutral. Or I should say, you're pulling a hydrogen ion, which is positively charged, from something that is neutral. In the case of the second dissociation, you're pulling another hydrogen ion from something which is negatively charged. So as you can imagine, if you're pulling something which is positively charged from something which is negatively charged, that's more difficult, right? And therefore, as a result, that dissociation is relatively weak. Okay, going back to the PowerPoint now. Okay, so strong electrolyte, weak electrolyte, strong acids, which are strong electrolytes. And then we're going to talk about weak acids, which are weak electrolytes. We met one example of a weak acid before, that's acetic acid. But here's another one. Hydrofluoric acid. It is weak. It will undergo partial dissociation, as you can see in this equation right here. The partial dissociation, of course, is represented by the fact that you have the back and forth. So basically, you're going to have an equilibrium achieved eventually. All right, so here's another one, nitrous acid, another weak acid. And the hydrogen sulfate ion, which I showed you earlier, that can be considered to be a weak acid as well. And water itself is a weak acid. We saw that earlier in the case of auto ionization, right? So basically, all of these produces hydrogen ions, but the dissociation is weak. In other words, the equilibrium basically favors the reactants and not the products, all right? So as far as strong bases are concerned, these are strong electrolytes which will undergo complete dissociation. Typically, strong bases are hydroxides of metals, such as sodium hydroxide, as shown here, potassium hydroxide, and barium hydroxide. These are strong bases, right? They undergo complete dissociation to form hydroxide ions. Okay, so weak bases are weak electrolytes, and they undergo partial ionization. As we can see here, for example, the fluoride ion is considered to be a weak base because it produces hydroxide ions, but it goes back and forth. So therefore, again, you're going to have an equilibrium system, all right? The nitrite ion also is considered to be a weak base. And when it comes to the relative strengths of acid-base pairs, right? What you'll find is that the conjugate base of a strong acid has no measurable strength. So therefore, basically, if you have a strong acid like hydrochloric acid, then the conjugate base, which would be the chloride ion, will be basically weak, so weak that it has no effect on water when it's added to water. All right. Another thing about conjugate acid-base pairs is that the hydronium ion, and that is one specific conjugate acid, is the strongest acid that can exist in an aqueous solution. And the hydroxide ion is the strongest base that can exist in an aqueous solution. So basically what we're saying by these two last statements is that if you have an acid which is stronger than water and you add it to the water, then what will happen is that that acid will dissociate so that the only strongest acid remaining in the solution will be the hydronium ion. And in the case of the base, if you add a strong base to water, then that base will dissociate, and therefore the strongest base resulting in that solution will be the hydroxide ion. And in chemistry, we call this the leveling effect. Write this down here. The leveling effect. The leveling effect is basically the effect that a solvent will have on the acidity of the acid or base that's added to it, right? If the acid or base is strong, stronger compared to that of water, then basically in the case of an acid, it will dissolve in water and dissociate to form H0 plus, right? And if the base is strong, then when added to water, it will dissociate to form OH minus, because those are the ions that can exist as the strongest acid in the case of H0 plus, and in the case of OH minus, the strongest base in an aqueous solution. And here we have a list of acids on this side of the table, and they are arranged in order of increasing acidity going from bottom to top, right? So remember, these are the 6 acids that you need to remember, right? These are the strong acids, right? These are the strongest acids in this list, followed by hydronium, and then below that you see some other weaker acids, right? And what you'll find is that when you compare the strength of your strong acid to the conjugate base, as I said before, if the acid is strong, then the conjugate base will be relatively weak, right? So as you can see, here we have the list of corresponding conjugate bases, and therefore the base strength increases as you go from top to bottom, all right? So perchloric acid is the strongest acid. The perchlorate ion will be the weakest base, right? On the other hand, ammonia is the weakest acid. The amide ion, which is what happens or what is formed when you remove a hydrogen ion from here, the amide ion will be the strongest base in this list, all right? So that gives you an idea as to the relative strength of the acid compared to its conjugate base. And we can actually measure the acidity of these acids and bases, and that we'll get to later on. This is just a pictorial representation of the difference between a strong acid and a weak acid. So as I said before, in the case of a strong acid, it will undergo complete dissociation. So if you're starting off with HCl before ionization, you add it to water, then what will happen is that you will see only H plus and Cl minus present. You will not see any intact HCl molecule present in the acid solution, right? On the other hand, in the case of hydrofluoric acid, which is a weak acid, when you add it to water, only a small amount of HF will be converted to H plus and F minus. So as you can see here, the concentration of the HF decreases slightly, and basically you're going to end up with a low concentration of the ions formed, all right? So that's the difference being shown here between a strong acid and a weak acid in terms of the level or extent of dissociation when they're added to water, all right? Okay, okay, so let's answer this question. This example, the question says, what is the pH of a 2 times 10 to the minus 3 M nitric acid solution? Now, when you're asked to calculate the pH of an acid solution or a basic solution, the first thing you have to ask yourself is this acid a strong acid or weak acid, or strong base or weak base, right? In this case, we're dealing with an acid. So we have to ask ourselves the question, is this a strong acid? And remember I said you need, and this is the reason why you need to memorize those 6 acids, right? So in this case here, if your memory is working, you remember that the nitric acid is a strong acid, right? So what does that mean? That means that when nitric acid dissociates, it undergoes complete dissociation, right? There's no equilibrium set up. There's no back and forth between the products and reactants. Basically, you only have this and this present. So what does that mean? That means that whatever the concentration of this that you're starting off with, the concentration of H plus is going to be the same, right? So we can say that the concentration of HNO3 is equal to the concentration of H plus, which is equal to 2 times 10 to the minus 3 m. So the pH, by definition, is minus log of 2 times 10 to the minus 3. So let's see what that gives. 2 times 10 to the minus 3. And then we find the log of that minus, and according to my calculation, this is equal to, we have to round this off to 1 decimal place. So this would be 2.7. That's how you do that. All right. Any questions about this one? Any questions? Admittedly, this is a relatively easy example. Let me just skip all this here. Okay, let's look at this one. What is the pH of 1.8 times 10 to the minus 2 m barium hydroxide? Now, in this particular case, barium hydroxide is a strong base. All right, so when that dissociates, it's going to form Ba 2 plus 2OH minus, right? Now, they gave you the concentration of barium hydroxide to be equal to 1.8 times 10 to the minus 2. So basically, if the concentration of barium hydroxide is this, then the concentration of the hydroxide ion will be 2 times that value because of the 1:2 ratio between the barium hydroxide and the hydroxide ion. So therefore, we can say that the concentration of OH minus is going to be equal to 2 times 1.8 times 10 to the minus 2 m, which is equal to 3.6 m. I'm sorry, 3.6 times 10 to the minus 2 m. So therefore, POH is equal to minus log of 3.6 times 10 to the minus 2 . And according to my calculation, this works out to be equal to, now in this case, we have to round off to 2 decimal places. So this would be 1.44. And that's how that is done. Okay. Before I forget, let me get everybody's attendance. See who came in late. Is Bharat here? Bharat?
Yeah, here.
Okay. Bessie,
Here.
Kylie, Medina. Let me check online. I keep forgetting to do that. Okay, she's not here. Monsieur is here. Olano. Bencha Pagana.
Here.
And Wright is here. Okay. Okay, continuing. What time is it, by the way? Okay. So continuing, all right. Come on. Oh, pH. That's what the question is asking for. So there's one more step we need to take. What's that one more step? For this question.
14 minus 1.44.
Right, so pH is equal to 14.00 minus 1.44, and that would give what? 12.56. Okay, so that, whoops. So that's the pH of the solution that the question is asking. All right, let me scroll down. Okay, now let's go back to the assignment before we do ionization constant. Okay, so let's see here. So let's look at question number 4, which says, what is the pH of a solution that contains 25 grams of HCl dissolved in 1.5 liters of water? Okay, so let me hear some ideas as to how you'd approach this. Remember now, the pH by definition is equal to let me just put that over here. pH is equal to minus log the concentration of H plus or H3O plus. Okay, so how would you calculate the pH based on the information which is provided here? They gave you the mass of the acid and they gave you the volume of the solution, the volume of the water. So what would you do firstly?
Find the moles of HCl.
Okay, let's do that. So we'll find the moles. So it's 25 grams. What do you multiply that by? What goes up top here and what goes down here as a denominator?
Top is 1 mole.
1 mole of HCl, and down here would be what? Okay, so let me, you all know me how lazy I am, so let me go to my molar mass calculator. Okay, so we're talking about HCl. And according to this, 36.46 grams is the molar mass. 36.46 grams, all right? All right, so now that we have the molar mass and we can calculate the moles, what would be the next step?
Moles divided by.
Okay, 1.5 liters, right? And this would be the concentration of HCl, right? So let's see what that gives. 2.5 divided by 36.46, and then divided by 1.5. And according to my calculation, this works out to be equal to 0.46 M. Okay, what's the next step? By the way, what kind of acid is this? Is this a strong acid or a weak acid?
Yes.
Strong acid. So what do we know about strong acids?
Complete dissociation.
Right. So therefore, what can we say about the concentration of H plus formed from this acid? Because that's what we need to calculate the pH, right? We need a concentration of H plus. So
So the concentration of HCl.
exactly. So this would be equal to the concentration of HCl, right? So therefore, the pH would be equal to what?
Log
Minus log of 0.46. So let's see what this gives. 0.46 log, and then the minus sign in front of that would give, okay, according to my calculation, 0.34. And that's how that is done. All right, any questions about this one? Any questions? If you understand number 4, you should be able to do number 5. So let me hear what you have to say about number 5. And by the way, you guys out there in Zoom, feel free to chip in. Oh, somebody. Oh, all right. Yes, feel free to make your commentary, make your contributions to this discussion. So how would you do number 5 based on what we did in number 4? find the,
moles of nitric acid,
okay, so how do we do that?
32 grams.
1.32 grams times 1 mole over the molar mass. So let me go to my calculator again. HNO3, whoops, really. 63.01, so that goes right here. 63.01 grams. All right, what next?
Put that over liters.
I'm sorry?
Do you put the answer over liters?
Okay, so,
Well, you need to take the 750 milliliters and convert it to liters.
okay, I heard him. Repeat that?
Take the 750 milliliters of water and convert to liters.
Exactly,
And then
so,
divide.
and then you do the division. So what I would do here is, down here, I'm gonna put, as she correctly said, 750 mils. Convert that to liters. 1 liter over 1,000 mils, all right? So that's what I would do to calculate the molarity. So let's see what this gives. 1.32 divided by 63.01 divided by, that's gonna give 0.75. So according to my calculations, this works out to be equal to 0.0, how many sig figs? 2 sig figs, 0.028 M, all right? So what's the next step?
With a strong acid or weak acid?
Exactly, so this would be, the concentration of HNO3 would be equal to the concentration of what? H plus, because it's a strong acid, exactly. So pH would be equal to what? Minus log of 0.028. So let's see what that gives. 0.028 log minus, okay. So this I have to round off to 2 decimal places, which is 1.55. And that's how that is done.
Is there a unit on that?
No, no units. And thank you, I should have mentioned this before. There are no units associated with pH, right? In some textbooks, they will say something like pH units, but that's not necessary, right? So you can just leave no units. There are no units associated with pH or pOH, or for that matter, any of the P's that you're going to meet later, or we're going to meet some other P. There's pKa, pKb. I'm not sure about PKSB, but I'm quite sure that exists. But you're going to meet some other P's later on, all right? Okay, any other questions about this? Any other questions? Any other questions? Okay. Number 6, let me clear this. Let's scroll down. Okay, now number 6 is a very interesting question because you're making an acid solution using 2 acids, right? One of them is nitric acid and one of them is hydrochloric, and they gave you the moles of each, right? And they're all dissolved in 1,000 liters of water, all right? So the question is, what's a pH? So let me hear what ideas you guys have in terms of solving this particular problem. They gave you the moles of nitric acid, they gave you the moles of hydrochloric acid, and they gave you the final volume of the solution. So again, you have to ask yourself the question, what type of acid we're dealing with? Strong acids, right? Hydrochloric acid is strong, so hydrochloric acid will dissociate completely. Let me do it here. HCl will dissociate to form H plus Cl minus. And the same is true for nitric acid. HNO3 will dissociate completely to form H plus and NO3 minus. Okay, so now that we know that to be the case, how would you determine the pH again, which is equal to minus log of the concentration of H plus, right? How would you determine the pH of this solution?
You add the 1.2 and 1.7.
Exactly, because whatever the moles of nitric acid is, the moles of H plus coming from that would be the same because of the complete dissociation. And the same is true for the hydrochloric acid. So what I'm going to write down here is that the total moles of H plus would be equal to the total moles of of the mixture, let me just say the mixture. Right? Or let me just say HNO3 and HCl. All right? So what does that mean? That means that that would be equal to 1.2 plus 2, 1.2 moles plus 1.7 moles, and that's going to be equal to 2.9 moles. Okay, what next? Now that we have the moles, 2.9 moles,
Divide it by 1,000 liters.
You find
Oh,
the
what?
concentration. You find the concentration.
okay, so to find the concentration of H plus, we divide by what?
1,000 liters.
2.9 moles divided by 1,000 milliliters, which is the same thing as 1 liter. So 1 liter over 1,000 mils. And that would be equal to 2.9 M. All right. But we're not finished yet because the question is asking for the pH, right? So the pH is equal to what? Oh, I'm sorry, not 2.9 M. 2.9 times, no, what am I saying? 1,000 liters. My bad, my bad, my bad. What am I doing? Okay, so 1,000 liters. So that would be equal to 2.9 times 10 to the minus 3 M. All right? So, what's a pH?
Negative log
Minus log of
2
2.9 times
10 to the negative.
10 to the minus 3. And that would be it. So let's do that here. 2.9 times 10 to the minus 3. And then I do the log. And I'll round off to 2 decimal places. So that would be 2.54. And that would be how we would determine pH of that solution. Yes, sir.
You do 2.9 mole divided by 1,000 liters, wouldn't it be 1 sig fig?
Normally, yes, but I think actually I think it's a typo. So just put a decimal point here, and that will take care of the sig fig issue. All right. Any other questions about this? Any other questions?
Explain why you added the moles again.
The question says that you're mixing 1.2 moles of one acid to 1.7 moles of the other acid, right? Both acids are strong acids, right? So whatever the number of moles of nitric acid that's there, when added to water, is going to produce the same number of moles of H plus. And the same is true for the nitric acid. So that's the reason why we add those two together. All right? Okay, any other questions? Any other questions? What time is it? Okay, we have 10 more minutes. Okay, we can do number 7, then we're going to stop here. Number 7 says, if a solution has an H plus concentration of 4.5 times 10 to the minus 7, is this an acidic or basic solution? Hmm? It will be acidic because remember we said in an acidic solution, the concentration of H plus would be greater than 10 to the minus 7. 1.0 times 10 to the minus 7. And this is definitely greater than that, right? So the answer is that this would be an acidic solution. Because concentration of H plus is greater than 1.0 times 10 to the minus 7 M. And that's it. All right? Okay, I think we're going to stop here for today because the next question, let me see what the next question. Yeah, okay, I'm going to stop here for today and leave that until next class. All right? Okay, so remember the assignment number 3 is going to be due tomorrow. So make sure you submit it then. And I think that's all I have to say about wrap it up. All right, so I'll see you guys tomorrow.
I know. How comes the significant figures is 3.5, but wouldn't it just be 6.5?
Point nine.
Or no, for.
Oh, so you did it differently.
Yeah, that's.
Okay, okay. No problem. You should get the same result.
I just added.
So when you added these two, what did you get?
2.5.
No, I can't take the instruction.
No, I mean, not before you do the law.
Because I just took this,
Yeah, I understand what you did. Yeah, I'm sorry, the concentration.
Yeah, because I knew these were plus, so I just.
I'm just gonna keep on going every single day.
And then. Right, I got the same thing, and then you would leave it out. Right, so the answer should be 2.54.
It's okay if I put it.
Because you're gonna have two sig figs here when you add these two. So that means you need two decimal places, so. So,
I got it back today, but we'll look.
yeah, so that should be 2.54. Yeah, I mean, that way is just as legitimate as what I did. Yeah, yeah. Yes, ma'am.
Oh, I think also the PowerPoint, it didn't upload yet, but I was able to write to the company tomorrow. Yeah, I was choosing, yeah, I was able to.
So there.
But it's the answer. I got like,
4 points.
got 260, and then the answer I put zero.
It should be here.
The holes are wrong.
You go to lecture notes.
Yeah, I only see the
Yeah, I got
kinetic chapter.
It should be right here. I just published.
Oh, yeah.
Published right here.
Yeah, what you said.
You see that green check mark?
Yeah,
That means published, so.
I wrote.
I don't know what is happening from your end.
It's on chapter 12, chapter 13.
Hmm,
Right.
Maybe you just have to refresh it.
yeah, refresh the page and see.
But then I had another question. For this one, can you explain again what you meant by the safety being the same?
Okay, so basically, whenever you're applying the log function to a number, right? Like in, okay, let me show you this. So basically, whatever the number that, when you do 10 to the minus, whatever, right? Whatever the number of decimal places that you have here, like here is 2, and then the number of sig figs must be rounded off to 2 sig figs. Right,
Yeah, so it's one of the answer.
right. Now, the thing is, I think I showed you, let me,
Yeah, I'm sorry. I didn't have the copy, so I was writing.
like in this case,
Yeah, okay.
right? You have 2 sig figs here.
Right.
That means when you do the page, your answer must be rounded off to 2 decimal places, right? So, and this is true whenever you're applying the log function for a number, right? The number that you're applying the log function to, whatever the number of sig figs in that number, then the result should be rounded off to the same number of decimal places. Right? And the reverse, of course, you understand what happened.
Then one more question.
Yes,
For
sir.
the lab, so I make sure I'm on the right one. It's the kinetic, yeah.
Yeah.
Thank you.
No problem.
Okay.
Yes. Have a good one. See you later.
Yeah.
Well, I got that, I just didn't.
What's up? What's up? What's up? What's up? I need to go.
I was looking at the, yeah,
Uh-huh.
that 0.737 or?
So?
0.7.
Because it was 27.
I think it's 0.737.
On my exam, I got the same answer, but. Marked up.
So divided by 40. Or actually, it should be 4. 0.734. Yeah, I think yeah. No, 0.734. That's 6. Oh, I'm sorry. Yeah, 7.
Yeah.
Yeah, all right. So,
We got 1 point marked up.
okay, we'll see. Oh, the reason why is because you didn't show where you got the 0.403 from. You see this question mark? You see this question mark with the arrow?
Oh, I didn't show how I added the.
Right, exactly. Yeah.
Also, you gave me a 75% for the exam when my grade was actually 93%.
effort to actually sign into the.
I think you mostly got me confused for Medina class was just.
I know there are two of you guys. Let me see here. Okay, so. Okay, so,
Probably.
what? You're right.
I think the closest one to me is like 30 to 45 minutes. Like towards Venice, yeah.
Okay, so I just changed it. Mhm. What's up?
I want to have some good graph.
Okay, not bad, not bad, not bad. This is exactly what I was looking
That's what you
for.
had in mind.
Yeah. Not
Alright,
bad.
and then one question was, so I put the initial concentration.
Right? No,
Would it be fine?
should be the final.
I made two just in case. I have the final.
Yeah, I didn't look at that, but I mean, it should turn out to be the same.
It's, yeah, it's the same. It's just the
But-
X thing.
Yeah, so make sure this is the final.
What did you use to graph?
Google Sheets.
Okay.
What's
Excel,
that? What did you use?
Google Sheets. Excel, I had no idea how to work Excel.
Yeah.
I tried for like 3 hours.
Oh, really?
Yeah.
Sheets, mine turned out like this.
Let me see.
Yeah, 0.06.
You did Google Sheets.
Yeah.
Yep, but you should have a straight, you should have a line of best fit. I've never used, that before. I probably need to check it out. But, you need,
That's more like how it's supposed to look.
exactly.
But,
So you use what?
Google Sheets.
Oh,
Oh, it's because you had the same X values, because like the concentrations were different. Cause see, like this one was like 0.06 and this one was like 0.09,
well,
right? Because you had like both of them.
Well, I put it in as different concentration. I don't know. how-
did you, well,
Yeah.
it should be straight, it should be like what he has here, because this is for the acid and that's for the sulfate.
Can I
You pro-
see how you have it
Yeah,
set
yeah,
up?
yeah.
Probably need to
Yeah.
consult him. Because I have no idea.
Probably the way I have it set up. I have time to figure it.
Do on my.